If you have reactions that involve many different types of species, gases, liquids, aqueous, things like that, concentrations of pure solids and concentrations of pure liquids do not change during the course of the reaction. They are not in a solution, they are pure. And so therefore we leave them out of the equilibrium constant. So for the reaction of carbonation, carbon dioxide and water produce H plus and HCO3 minus 1, the equilibrium constant will not include water. The Kc would be H plus concentration times HCO3 minus 1 concentration divided by the concentration of carbon dioxide. When we want to find an equilibrium constant, the best way to do that is to measure the amount of reactants and products at equilibrium. Very much a plug and chug type calculation. If you have the concentrations of each reactant and product at equilibrium, then you can find K. The equilibrium mixture may have different amounts of reactants and products, but if the value of equilibrium is the established values that you're getting, the equilibrium constant will always be the same no matter what those values are, as long as the temperature is kept constant. These are temperature dependent reactions. But the K, equilibrium constant, is independent of initial amounts of reactants and products, meaning no matter how much you throw in of the reactants, no matter if it's 5 molar, 10 molar, or you go big or go home and you put like 19 molar of an initial reactant in there, equilibrium will always be established with the exact same equilibrium constant K, as long as your reaction is at the same temperature. Stoichiometry can also be used to determine the equilibrium concentrations of all the reactants and products if you know an initial concentration and at least one equilibrium concentration. You can use the change in concentration of the material that you know to determine the change in the other chemicals. Remember, we're balanced here. And so we're going to practice with that and see what type of data we can utilize to calculate K, the equilibrium constant. Let's look at this reaction. Carbon monoxide and hydrogen gas are in an equilibrium to produce CH3OH, methanol. The reaction mixture at 780 degrees Celsius initially contains carbon monoxide at 0.5 molar, hydrogen at 1.0 molar, and at equilibrium, the carbon monoxide concentration is 0.15. What is the value of the equilibrium constant? Let's start by writing the expression, the law of mass action. Let's write that equilibrium constant K. Product CH3OH to the first power divided by carbon monoxide times hydrogen squared. All right. Now, the original values we are given are initial. They are not at equilibrium. We're going to set up something called an ICE table. I stands for initial. What are the initial concentrations? C stands for change. What's the change in concentration to reach E, equilibrium? We will be practicing with these ICE tables for the rest of this chapter. They are very, very handy in determining equilibrium concentrations. So now I want to be able to write in my ICE table carbon monoxide concentration, hydrogen concentration, and CH3OH, methanol concentration. Now to start us off, carbon monoxide started at 0.500 molar. Hydrogen started at 1.00 molar. Methanol starts at 0. Not written, it's because we start with no products based off of the given information. At equilibrium, I know the carbon monoxide is 0.15 molar. Now, from that amount of information, I can determine the change. I know an amount of carbon monoxide decreased. That same amount, but times 2, would decrease for hydrogen. Now, where did I get that times 2? For every 1 mole of carbon monoxide, 2 moles of hydrogen gas must be used. And I know however much those molecules decreased, my methanol must have increased. So what I'm looking at here is a stoichiometric relationship of the changes in concentration that occurs when this reaction starts to reach equilibrium. Now, because I've been given this value of an equilibrium concentration, I can calculate using algebra x. X is equal to 0.35. The change in concentration that occurs to reach equilibrium is 0.35 for carbon monoxide, 0.70 for hydrogen, and positive 0.35 for methanol. The biggest thing here is when finding the change, do not forget the stoichiometric relationship of the balanced chemical equation. And now I can find the equilibrium concentrations for all of the other components. All right. Now it's a matter of plugging in these concentrations to Kc. 0.35 molar divided by 0.15 molar divided by 0.3 molar squared. Yes, that square still needs to be there. You have to count it in the change column, or the change row, excuse me, and you also have to count it in the equilibrium expression. All right. 26, unitless value. What does that tell you? Well, it weakly favors products. For every 26 products, I will have 1 reactant left over. So we do favor products here. We can even write this in scientific notation, 2.6 times 10 to the 1. We see a positive value in the exponent, so therefore we favor products, all right? Because K is greater than 1. Now the reaction quotient Q is utilized if a reaction mixture contains both reactants and products, but is not at equilibrium. It's a method of being able to, at a specific moment in a reaction, calculate via the concentrations given, which direction will the reaction proceed. And it's about calculating Q just like we would calculate K, but we're not at equilibrium, so we can't call it K. We have to call it something else, and we call it the reaction quotient, or Q. Now, the answer is to compare the current concentration ratios to what we expect for the equilibrium constant. The concentration ratios of the products, raised to the power of their coefficients, divided by the reactants, raised to their power of coefficients, is the reaction quotient Q. You're going to say, Lauren, that's exactly what you just told us before. Products divided by reactants. Yeah, it's the same calculation, except for it's not at equilibrium, so we can't call it K. Otherwise, we'll get very mixed up. Yeah, it's the same thing. I know. But we already know that Q, why we need to use Q, is to establish that we know we're not at equilibrium. If Q is greater than K, we know that there are too many products. A greater Q tells us the numerator is too large. So the products will start to decrease, the reaction goes in the reverse direction. If Q is less than K, too many reactants. The denominator of Q is too large. So the smaller Q means the reaction needs to proceed forward and make more products. Only if Q is equal to K, then we can say we are at equilibrium. The products and the reactants will not change, and therefore the reaction is going to already be established at equilibrium. If a reaction mixture contains just reactants, then Q is 0, right? Because there would be 0 products. The numerator would be 0. We know that that would mean Q is less than K. So the reaction proceeds forward to make those products. If the reaction mixture does not contain any reactants, the denominator is 0, then Q is essentially infinity, right? And the reaction then would proceed in the reverse reaction. We know equilibrium will be established when there is both reactants and products in the reaction mixture. The rates of the production of those reactants and products is constant. This is a nice chart to start establishing where is equilibrium. If we plotted a concentration of a reactant, notice here, B is at 0, and we're saying, let's ramp up and make more B, make more B, make more B. If we overshoot, we got to go backwards, right? And be able to find that equilibrium when Q is equal to K, when the reaction mixture can say, I'm done. The rate of my forward is equal to the rate of my reverse. Let's look at this last example. I2 plus Cl2 yields 2ICl. The Kp is 81.9. The reaction mixture contains a partial pressure of iodine at 0.114 atm, partial pressure of chlorine at 0.102 atm, and a partial pressure of product, ICl, at 0.355 atm. What's going on? Is the reaction mixture at equilibrium? The only way to tell is to calculate Q. Product, partial pressures, product over reactant. Let's plug in the values we have. 0.355 squared over 0.114 times 0.102. Now, we get a value of 10.8. Let's look at that value. Q is less than Kp, call it Qp. What does that mean? Since Qp is less than Kp, the reaction is not at equilibrium and needs to proceed to the right, needs to go forward. Make more products. We need that numerator to be larger. Excellent.